So I've chosen this problem from the Serway book, chapter 29. And rather than read it for you, I'll let you pause the video and read it yourself. See if you can get started on how you might approach this problem. Well, first step to get started with the problem is to circle the things that you know, the important information, and try to identify what the target variable is. So in this case, I circled the few things we know. We know there's the diameter of the blood vessel, 3 millimeters. We know the magnitude of this magnetic field pointing from left to right, from north to south. And we know the magnitude of the voltage being read by this voltmeter here is 160 microvolts. The target is calculate the speed of the blood, so we want to know how fast the blood is flowing. It's really nice that the diagram has been drawn for us, but sometimes because it's three-dimensional, it's easier for me at least to draw it in 2 dimensions, so I don't have to kind of think about in 3 dimensions like that. So I'm just going to redraw this diagram in a way that's a little bit easier to process. So I'm going to draw it edge on. I'm going to draw this. Here's going to be the big blood vessel. So we're looking edge on. Imagine the velocity of the blood is coming out of the page. So the blood is rushing out of the page towards you. We've got our magnetic field looking like this. So here's north, here's south. And the magnetic field points from north to south. So in the middle of this blood vessel, there's going to be a magnetic field pointing to the right. Then we have a voltmeter hooked up to the top and bottom of this thing, like this. And it's measuring a voltage difference. So I'm going to try to draw it like this. So this goes to a voltmeter, which measures delta V. The top is positive, the bottom is negative. So there's a sort of redrawing of the diagram in a way that's a little bit easier to understand. So now let's start thinking about the physics involved in this problem. We've got a voltage being developed because there's a flow of something through a magnetic field. If you read the problem, it says for a magnetic field magnitude of 0.40 Tesla, an EMF of 160 microvolts appears between the electrodes. So that voltage does not appear unless you put this blood vessel in the magnetic field. So it's a voltage that develops because of a magnetic field. And so it's due to the interplay of electric and magnetic fields, and that should remind you of a particular effect. That's the Hall effect. So this is a Hall effect problem. A voltage is developing because you have something moving in a magnetic field, and of course the thing that's moving has to be charged particles. So now let's remind ourselves, it's probably a good time to remind yourself of the story of how this Hall effect goes. I can't have the Hall effect without charged particles, so there's got to be charged particles in the blood here. So I'm going to just draw them like this, and I'm going to pretend they have positive charges. We'll think about if the answer would change if they have negative charges later on, but let's say they have positive charges. They're flowing along with the blood, so they're moving out of the page. Their velocity is out of the page, and there's a magnetic field pointing from left to right. So what are the forces acting on these particles? Velocity is out of the page, magnetic field is to the right. Why don't you pause the video and see if you can determine the magnetic force on these charges. Okay, did you make your prediction? If I use the right-hand rule, the fingers of my right hand come in the direction of V out of the page. I curl my fingers in the direction of B, which is pointing left to right. I get a force which points upward. So you should see that these particles will experience a magnetic force upwards, right? FB. So this is what happens initially. Let me call this initial situation. Is the charges are coming through into this magnetic field, and they feel a force upward, and as a result, they get pushed upward. But that's not the whole story. So now you have to think about what's going on after that. On the previous slide, we discussed what was initially going to happen with charges coming through this magnetic field. They feel a magnetic force upward, assuming they're positive charges. Now, so all of those charges which I drew on the previous slide are going to get pushed to the top. So those positive charges get pushed to the top. By extension, the bottom becomes negative because the whole thing started out neutral. If I push the charges, the positive charges one way, the other way is going to be the opposite, going to be negative because I lost all the positive charges there, right? So I get this buildup of charges. Those are the charges, the ones I just drew are the ones from the previous slide that got pushed to the top. Now I've got a separation of charges. I've got a plus on the top and minus on the bottom. So there's an electric field which develops. You know this. Right? You know that there's an electric field which goes from plus to minus. So there's an electric field which is developed, which we call the Hall electric field. And this voltage here is called the Hall voltage, delta VH. That developed because of the magnetic force which separated the charges. Now, the key point is that if you now, this is going to keep happening, right? This electric field is going to get bigger and bigger and it's separating more and more charges until what? Until, imagine now I put a different charge coming through here. It's still going to be positive. That magnetic force is still there, right? There's a magnetic force pushing upwards, FB, because the magnetic field is still there. But there's positive charges at the top. It repels other positive charges. It feels an electric force downward, right? That electric force is counteracting the magnetic force. And once I've separated the charges enough, eventually those two forces cancel each other out, and then I've come to equilibrium. So my final, or my equilibrium situation is when the magnitude of those two forces, the magnetic force upward in this case, is equal to the electric force pointing downward. So this is the main thing that I remember when I'm doing Hall effect problems, is that it's really a balance between the electric and magnetic force. The magnetic force starts the charges separating. As the charges separate, I get an electric force, and the charges keep separating until those two completely cancel each other out, and then I can't separate any more charges. That's the main thing I remember about the Hall effect. The other thing you might remember is if you're good at memorizing or using your equation sheet, you'll notice that there's this equation, delta VH is I B over NQ. And what goes here depends on which textbook you look at, either T, I'm going to call it T. This T is a thickness, and N is a number density of charges. So those are the two. I mean, the second one is maybe the one main equation for Hall effect, but I like the first one best because it kind of encodes the story of what's going on. It's not just plugging numbers into an equation. So we have the physics that we're going to use. We've reminded ourselves of the story of how the Hall effect works. It's time to start planning a solution. I can think of two approaches, both based on those equations that I wrote on the previous slide. So the first one would be to use somehow the equality of the magnetic force to the electric force magnitude. The tricky part is that this doesn't seem to have the thing that we're looking for, which is speed in it, but then you remember that the magnetic force depends on the speed. So this is going to be Q V B sine of theta. Theta is the angle between the velocity and the magnetic field. And then the electric force is Q times E, right? In this case, sine of theta is 1 because theta is 90 degrees. The velocity of the charges in the magnetic field are perpendicular. The Q's cancel. We're almost there. We're trying to get this velocity here. The only problem is we don't know the electric field. But then we also need to relate the electric field to the Hall voltage, delta VH. And the way to do that is delta VH is equal to E times the distance over which that electric field acts, which in this case is the diameter. Let me call it a big D for the diameter. So that's the usual relationship between voltage and electric field in a uniform electric field. So we're going to combine those two. That's one way to approach the problem. The second way to approach the problem is you might think to just go to the equation sheet and use this formula. Delta VH is equal to IB over NQT. Now the problem is it doesn't have velocity in it, but then you could think, well, maybe I can use I is equal to NEA times the velocity. So second approach would be to try and do this. I'm going to use approach 1, and then at the end I'll come back and talk about approach 2 because there's a subtlety there that approach 2 actually will not work. So we'll proceed with approach 1 and then we'll come back to approach 2 later. So let's execute the plan. I invite you to stop the video and solve the problem on your own before you can check it with what I do. So go ahead and stop the video and see if you can work through the details now. Okay, so I will go ahead now and solve the problem. I just have to combine these two equations. So I need to remove E, which I don't know. Let's call this equation A and this equation B. So I'm going to remove E from A using B. So pretty simple. V, B, sine of theta is 1 is equal to E. And then E is going to be delta VH, Hall voltage, divided by D, the diameter. And now we can solve it. V is equal to delta VH, magnitude, divided by B times D. There's our formula in terms of things that are given. And now it's just a matter of plugging the numbers into this and checking that it makes sense. So there's our final formula. All we have to do is plug numbers in now. If you haven't already done it, pause the narration and go ahead and do it, just to make sure that you're doing it right. I'm going to do it, but I'm going to also pause the narration just to make it go a little quicker. Okay, there it is. I converted everything into the standard SI units. And let's check the units, which is the first thing we should do. So I put everything in SI units. I should get SI units out, but it's a little tricky. You have to remember what a volt and a Tesla are. So I remember that 1 volt is 1 joule per coulomb. And a joule, remember, is a kilogram meters squared per second squared. Kilogram meters squared per second squared divided by coulomb. And 1 Tesla, the thing I remember, is 1 kilogram divided by coulomb seconds. So let's check now the units of V. On the top I have volts, that's kilograms, meters squared, seconds squared, coulombs. On the bottom I've got Tesla, kilograms, coulomb, seconds, times meters. Okay, so let's take a look now. There's a kilogram on the top and a kilogram on the bottom. There's a coulomb, a 1 over coulomb on the top and a 1 over coulomb on the bottom, so those are gone. On the top I have meters squared per second squared, and on the bottom I've got meters per second. This is all meters per second, which is the right units of velocity. So the units are good. Finally, we can just plug the numbers into the calculator and we can have confidence in our result. Plugging all the numbers in, I get that the speed is about 1.33 meters per second. There's your answer to part A. That's a reasonable velocity, by the way. Your blood is not rushing through your blood vessels at relativistic speeds, 1 meter per second. It takes blood about 1 second to go about, if I'm 2 meters tall, it takes blood a little more than a second to go from my feet to my head. That seems pretty reasonable, right? Your heart rate's about once a second. Seems pretty reasonable. So there's the answer to part A. So let me take a minute here to talk about approach 2. I mentioned that there was something wrong with doing this. So you might think, what's wrong with this? You might say, use the formula from the equation sheet. Delta VH is IB over NQ T. T is the thickness, which in this case is the diameter. And then I is equal to NQAV. If I combine these two, I get delta VH is equal to NQAV times B over NQ times the thickness, which in this case, the thickness is going to be the diameter of this cylinder, or this circle. Okay, what happens? N's cancel, Q's cancel, and I've got AVB over D. So I've got delta V is equal to D delta VH divided by A V B. Whoops, not B, just A times B. Now what is A? A is cross-sectional area. That'd be the area of this circle. So that would be D delta VH. The area of the circle is pi times the radius squared, which is D over 2 squared times B. And if you simplify that, you get delta VH. There's a 4 on top because there's a 2 squared in the 1 over 2 squared in the denominator. Pi D times B. And you see that this formula is a different formula than this one, the one we derived previously. They look the same, they've got delta VH over BD, but this one has some numbers, 4 over pi, which the one on top doesn't have. So what's going on? What's going on is this equation is wrong. So this equation here, which you take from an equation sheet, it's always good to keep in mind when things are valid. This was derived using a rectangular solid. If you go back to the notes and you look at how this equation was derived, it was derived exactly using the approach 1, using the balance of forces, and V is equal to E divided by B, and so on. So this formula, the way we first solved the problem was more fundamental, thinking about forces and the story of the Hall effect. Going straight to the equation sheet and using this formula is not as good because you don't know exactly when this is valid. It's better to start from the fundamentals rather than jumping right to an equation. So this is no good because we don't have a rectangular solid. We've got a cylinder, a circular cross-sectional area, and so this is wrong. But our first approach was right. This one is correct. That's a subtle point, and took me some time to actually figure out what was going on. So the first formula there is correct. Let's move on to the rest of the problem now. Let's think about parts B and C. These are conceptual questions. We can do them both together. Part B, explain why electrode A has to be positive as shown. We already kind of worked out the reason. If the charges are positive, we saw that they had an electric force, sorry, a magnetic force upwards, right? and that caused the top to end up being positively charged. What if the charges are negative? What happens? Now I've still got the same velocity. Velocity is coming out of the page because the blood flow is this way, right? That's not affected by what is in the blood. So the velocity is still out of the page. Magnetic field is still to the right. What happens to my magnetic force? Use the right-hand rule, V cross B. My thumb points up, but it's a negative charge, so I have to flip it over. So this has a magnetic force downward. It's a negative charge. The magnetic force flipped direction, and so this negative charge will get pushed to the bottom. The bottom will will be built up negative, and the top, of course, will end up being positive because all the negative charges got pushed down. Which is the same as before, right? This is the same as before. So we can answer parts B and C kind of simply. Explain why electrode A has to be positive as shown, so that if there's positive charges, FB is up, and so the top builds up positive. If they're negative charges, FB is down, which means that the top is positive in both cases. And so for part C, does the sign of the EMF depend on whether they're positive or negative? And the answer is no, for the same reason. No matter which case I have, the top of the blood vessel becomes positive, the bottom becomes negative. Before I finish, I want to mention something interesting about this problem. In parts B and C, we just argued that you can't tell the difference between positive charges in the blood or negative charges in the blood. But if you go to the lab, when we usually use the Hall effect when it comes to semiconductors, is it allows you to tell whether you have an N-type semiconductor or a P-type semiconductor. If you use the Hall effect with semiconductors, you can tell the difference between positive and negative charges, where in this problem you can't. So why is that? What's going on? How is this problem different than a usual kind of electric circuit problem? I'm going to let you think about it. Why don't you pause the video, see if you can figure out why that's different. And then I'll come back and explain it, but do try to think about it because it's kind of interesting. Okay, so did you figure it out? The difference between this problem and an electric circuit problem is what causes the flow of the charges. In this problem, it's blood flow, okay? So the heart is pumping the fluid is flowing, and the charges are getting carried along with the fluid. So I'm representing that up here. So I'm bad at drawing, so those are my hearts. The heart is pumping, it's pumping the fluid flow in this diagram from left to right. If I change the sign of the charges, their velocity is still left to right. Doesn't matter what the sign of the charges is. Velocity stays the same, in the same direction. Charge is different. However, an electric circuit problem, you can imagine your pump now is a battery. And in this diagrams, I've drawn the current flowing clockwise. If I change the sign of the charges, if the charges are positive, they're going to be flowing to the right up here. But if the charges are negative, if the current is flowing to the right, the charges will be flowing to the left. So in an electric circuit problem, because the flow of charge is flowing because of an electric potential difference, or an electric field, if I change the sign of the charges, I also change the direction of the flow of the charges. And that's why this problem is different from a circuit problem, and that's why in this problem you can't tell the difference between plus and minus, but in an electric circuit problem you can. It's a straightforward problem involving Hall effect with some subtleties. I hope you found the problem interesting and useful.